Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Baswakaland. The 30th session of Graph Theory 2. In this session, we are going to discuss some problems on crossing numbers. So that's the title of the session. Now already in the previous class, we have discussed what is the crossing number of a graph. So I think the crossing number of a graph is an extension of the planar and non-planar graphs, we can say. So planar graph, it is possible to draw without the intersection of edges. When there is no intersection at all, it implies there is no crossing at all. It implies crossing number is 0. So crossing number is 0 for planar graphs, isn't it? So therefore, for the non-planar graphs means there exists crossing, maybe one crossing or more than one crossings. Okay, so in that case there exists a crossing number 1 or more than 1. It implies definitely the non-planar graphs have crossing at least 1. Okay, so that was the discussion in the previous class. So again, if I recapitulate the definition of a crossing number is nothing but minimum number of pairwise intersections in the graph when it is drawn on the plane. So try to embed in the plane, but minimum number of crossings that we cannot avoid. So that number will be the crossing number. For example, if we consider K5 crossing number is 1. For the graph K33 crossing number is 1. So that already we have discussed. Okay, let me consider some more examples on crossing numbers. So the first problem, find the crossing number of the following graphs. As I said in the previous class, you just think over what will be the crossing number for the graph if it is a path with p number of vertices, if it is a cycle with n number of vertices, if it is a complete graph with p vertices, if it is a complete bipartite graph in the form of kmn. Okay, so those are the general concepts. Okay, what would be the crossing number of such standard graphs? Okay, yeah, if you find out the general result, so I think those results will be the standard results. As I said, there are only upper bounds for complete graph and upper bounds for the complete bipartite graph. The crossing number of complete graph and crossing number of complete bipartite graph. Till today, we cannot say exactly the crossing number of KP is so and so. Only upper bounds we know. So that's why we are considering some particular examples like what is the crossing number of a path with 5 vertices, what is the crossing number of a cycle with 7 vertices, what is the crossing number of a complete graph with 4 vertices. Can anyone guess? K4 is a planar graph. When it is planar, then the crossing number of K4 is obviously 0. K24 is also a planar graph. When it is planar, obviously the crossing number of K24 is also 0. So let me analyze this. It is known that P5 is a planar graph. If you consider a path with 5 vertices, it is obviously a planar graph. So when it is planar, the crossing number of P5 is 0. And C7, it is a cycle with 7 vertices. Cycle is also a planar. It is an outer planar graph. Any outer planar graph is also a planar graph. So when it is an outer planar graph or planar graph, then obviously you won't get any crossing at all. It implies again the crossing number of C7 is also 0. So like that you can think of Pn, Cn. What would be the crossing number? Okay. So this is how I have given you the idea. Now we will consider the graph K4. So already we know that K4 is a planar graph. When K4 is planar, then what you can say? The crossing number of K4 is again it is 0. And similarly K24 is also planar. So obviously the crossing number of K24 is also 0. So for any planar graph in general the crossing number is 0. So this is one particular example which we have considered. Let me consider the another problem. Prove that the crossing number of K5 is 1. Though already I said the plane embedding, if you try to embed in the plane, what happens? Okay, But let me prove this. The graph K5, first of all, it is non-planar, because we know K5 is non-planar. Even we have proved in the previous class K5 is non-planar. It implies when the graph is non-planar, obviously you will get crossings. How many crossings? At least one crossing you will get. It implies the crossing number of K5 is greater than or equal to 1. Okay. Now we observe that there exists a drawing of K5. If you try to draw the graph K5 without the crossover of edges, or if you try to minimize the crossings, actual graph K5 contains so many crossings. If you try to minimize the crossings, but one crossing you cannot minimize or you cannot avoid. So therefore what you can say, by the observation of this graph, so this graph K5 has exactly one crossing. So what is the conclusion? The crossing number of K5 is 1. So though I said it is a problem 2, but if you draw the K5 or if you try to embed in the plane or minimizing the number of crossover of the edges, pairwise edges, then you will come to know the crossing number of K5 is 1. Similarly, if we consider the another example, what is the other example? Again K33. You may ask the question, why repeatedly we are considering K5, K33? Because those are the least graphs. See, while characterizing the planar graph, what we said, a graph is planar if and only if it has no subgraph homeomorphic from K5 or K33. These are the least graphs with minimum crossings. Okay, so and while defining or while characterizing the planar graph, we have already mentioned these two standard graphs, the kurtosis graphs. Okay, so that's why repeatedly we are considering these two, because these are the, you can say, the lower bounds, these are the least graphs with at least one crossing. Least graph, any graph which contains homeomorphic with these two graphs, obviously it will be non-planar and it will contain at least one crossing, isn't it? So now to prove the crossing number of K33 is also 1, for that reason you have to consider or you have to prove the graph K33 is non-planar. First you have to prove it is non-planar. Once if you prove it is non-planar, then you can conclude the crossing number of that graph is at least 1, because there exists at least one crossing. Okay. Now if you draw the graph of K33, there is again one crossing that you cannot minimize. It is not possible to redraw. If you take a chance to join in this way, again you will get one crossing. Or is there any other way other than this? Even if you take like this, again there is a crossing. It is not possible. You have to cross at least one edge. This implies the crossing number of K33 is 1. So on the observation of this graph, what we can conclude, again the crossing number of C33 is also 1. So we have proved the crossing number of K5 is 1, even the K33 is also 1. Now we consider another particular example. Prove that the crossing number of K6, it is a complete graph with 6 vertices. Okay, so complete graph with 6 vertices, it implies first you will construct K5. Then you will take one more vertex. Okay, and you join that vertex to all other 5 vertices of K5. Then you will form K6. So it implies, first of all, K5 has one crossing. It implies K5 is homeomorphic from, K6 is homeomorphic from K5. So any graph which is homeomorphic from K5 is again a non-planar graph. And obviously you will get at least one crossing. But here you will get 3 crossings, because K5 itself has got one crossing, and if you construct K5, definitely if you try to minimize the number of crossings, even though you will get 3 crossings. Okay, so the graph K6 has a subgraph homeomorphic to K5. It implies what you can say, the graph K6 is non-planar, because any graph which is homeomorphic to K5 is non-planar. So therefore the crossing number of K6 is equal to, we don't know whether it is 3 or 4, say it is n. Now we consider a drawing of K6. As I said, how to draw K6? First you have to draw K5, then take one more vertex and join all other vertices of K5. But while drawing K5, try to minimize the number of crossings. So as you know, K5 has got one crossing. So for that graph, you have to join an edge between the new vertex and all other vertices. Okay. In that way, if you try to minimize, so what I'm going to say, consider a drawing of K6 in the plane with n crossings, because we don't know how many crossings we will get. At each crossing, we introduce a new vertex and produce a connected plane graph G with 6 plus n vertices. Okay, see, consider a drawing of K6 in the plane with n crossings. At each crossing, we introduce a new vertex. Wherever you are getting a crossing, there you have to introduce a vertex, a new vertex, and produce a connected plane graph G with 6 plus n vertices and 15 plus 2n edges. Okay, therefore the 15 plus 2n is always less than or equal to 6 plus n minus 6, which implies n is always greater than or equal to 3. Okay, so therefore the crossing number of K6 is greater than or equal to 3. Okay, let us the graph of K6, if you try to embed in the plane, it is not possible to embed, but try to minimize the number of crossings. So if we observe, there exists a drawing of K6 with only 3 crossings. This is one crossing, this is another crossing, this is another crossing. Okay, the drawing, the picture may not be in this fashion. If you draw in your own way, you may get in different form. Location of vertices and straightness is immaterial in graph theory. Okay, so but if you try to minimize, you will get 3 crossings. So what we can conclude, the crossing number of K6 is greater than or equal to 3, and on drawing the graph of K6, we conclude that the graph K6 has 3 crossings. So therefore the crossing number of K6 is equal to 3. Okay, so again in this session we have discussed what is the crossing number, and we took some examples or problems based on the concept of crossing number. As I said in the previous class, it is a challenging task to find the crossing number of a complete graph. It is a challenging task to find the crossing number of a complete bipartite graph. You may consider Kp. In general, I am saying. I am not saying K3 or K5 or K6 in particular. I am saying in general Kp. In general Kmn. Okay. So where 1 is less than or equal to m is less than or equal to n. In that way, if you consider the general graph, till today there is no any exact formula for finding the crossing number of a complete graph or complete bipartite graph. But we have got upper bounds. So there are results which shows that the upper bound means the crossing number of Kp won't cross this value. Okay, so we have got upper bounds in terms of the number of vertices. So those are the results. If you want, you can refer the graph theory by Harari. So in this book, Frank Harari, so graph theory by Frank Harari, if you refer this book, you will get such results where the upper bounds are given. But it is a challenging task to find a particular formula or a general formula to find the crossing number of complete graph as well as the complete bipartite graph. Exact crossing number you should get, not the upper bound. Okay, so with this we conclude today's session. Thank you.